Hey, welcome back. This is lesson 2 in unit 9 of AP Calculus AB. We are in a unit about solving differential equations. In the first lesson, we looked at a graphical way of solving them by drawing slope fields. In today's lesson, I hope to continue to connect back to slope fields because they're so important, while we look at some techniques we can use to actually solve a differential equation. A differential equation whose variables, that says show, should say, a differential equation whose, don't you love autocorrect, whose variables can be separated to two different sides of the equation are called separable differential equations. There are many different types of differential equations, and we have different techniques based on how they're classified and sometimes some overlap. We have already learned how to solve a differential equation where it's simply of the form dy dx equals f of x. But now we're looking at a different type of differential equation where it's dy dx is a function of x and y, but where the x and y variables are separable. Not every differential equation is like that, but the ones that we can solve in this class will be. The technique used to solve separable differential equations is called separation of variables techniques. And just a quick caveat, there is the term separation of variables goes beyond just these kind of equations. They even get into some really big equations that we won't be looking at. So if you're Googling for tips on separation of variables, just make sure you're getting help on a Calculus 1 or Calculus AB course, not some other more advanced course. All right, so example 2.1, we have dy over dx equals 2x over y. Let's study the slope field for this differential equation. As I look at it, it appears to have some branches of some hyperbolas, all right? If it was just a function, we'd expect it to only be half of that. Let's find dy dx at the point 1, 3. Well, we could look at our slope field and get a guess. It appears to be somewhere around maybe a half, but let's find out. So to find the exact slope at 1, 3, I simply evaluate there. dy over dx, or dy dx, is equal to 2 times x over 3. So it turns out that it's 2/3. Let's sketch the solution with an initial condition of y of 1 equals 3. So if y of 1 is equal to 3, it appears that there would be the curve going in this way until it reaches here and it starts to curve up and go around that diagonal. And here is where it's flat, and then curve back up towards this diagonal. Next, let's solve the differential equation given that y of 1 equals 3. So now we're going to go try and really hunt and find this answer. All right, so let's do separation of variables. So we want to get the y with the dy and the x with the dx, and they have to be multiplying. Everything has to be multiplying or dividing. You can't have adding separating the two. So if I multiply both sides by y and dx, or do the cross product, this separates pretty simply. I'll write y times dy equals dx times 2x. Next, I simply integrate both sides. And so on the left, I'm integrating with respect to y. I need to follow what this says. The integral of y dy is y squared over 2. And the integral of 2x is x squared over 2. 2 over 2 becomes just 1, and then plus c. Technically, I should have added a plus c on the both sides, giving me something like y squared over 2 plus, I'll call it c1, equals x squared plus some other c, I'll call c2. But then I could just simply combine those constants and have y squared over 2 is equal to x squared plus, now c2 minus c1 is some other c, I'll call c3. But c3 is just a c. So in practice, you can see, I didn't mean to be that punny, that we just need the c on one side. Okay, let's keep going with this. I'm going to multiply both sides by 2. So I get y squared equals 2x squared plus 2c, which is, again, just a c. Now, at this point, I'm going to go ahead and plug in my 1 and my 3. Y of 1 equals 3 means x equals 1 and y equals 3. So 3 squared equals 2 times 1 squared plus c. And I'm choosing to do this here because I like this equation like this. I don't want square roots and things like that yet. So I have 9 is equal to 2 times 1 squared. 1 squared is 1. 2 times 1 is 2. So I get c equals 7. So then I have y squared is equal to 2x squared plus 7. Now, we're actually, it doesn't say it very clearly in the instructions, but we're solving for a function that solves this. So we're actually going to take the square root of both sides. And that's where I have to choose plus or minus 2x squared plus 7. Which one should it be? Well, because I get a 3 when I plug in 1, I need to use the positive square root. So y equals the square root of 2x squared plus 7. That is my differential equation that results in that solution. All right, let's try the next one. Given y squared equals x squared times the square root of y. A. If y of 3 equals 4, write the equation of the tangent line to y at x equals 3. The tangent line can be written in point slope form like this. Y minus y1 equals slope times x minus x1, where m, the slope, is the slope of the tangent line. Well, that's exactly what y prime gives me. So y prime at x equals 3 and y equals 4. Remember, this is telling me that x is 3 and y is 4. Is equal to 9 times 2, which is 18. So my slope, the m, is 18. My x1 is my x-coordinate, which was 3, and my y1 is my y-coordinate. And so it's as simple as that. Very nice problem. We hope they ask it for us. It gives me the tangent line. Now let's solve for y as a function of x. This is the instructions you often get, telling us that we need to have it as a function, not just a relation, given that y of 3 is equal to 4. So first thing I'm going to do is I'm going to change the y prime to dy over dx. Y prime is good notation for some things, but dy dx is better for others, particularly when using separable differential equations. Since we're going to be separating it, it makes sense to write as dy over dx. In this one here, I'm going to divide both sides by the square root of y and multiply both sides by dx. So I'm multiplying by dx while I'm dividing by the square root of y. So it gives me dy over the square root of y equals x squared times dx. I hope that wasn't too complicated for you to see both of those steps at once, but I could spread it out if you prefer. So first I multiplied both sides by dx, and then I divided both sides by the square root of y. All right, I'm going to do some rewriting before I integrate here. And this is going to be the integral of y to the negative 1/2 dy equals the integral of x squared times dx. The integral of y to the negative 1, add 1 to the exponent, giving you a positive 1/2, multiply by the reciprocal, so times 2. And this becomes x cubed over 3 plus c. I will go ahead and multiply both sides, or divide both sides by 2, giving me y to the 1/2 equals x cubed over 6, and again plus a c. Now we were told, though, that if I can, let me scroll up right quick and find out. I believe it was that y of 3 is equal to 4. So I'll put a 4 right here. And 3 here. The square root of 4 to the 1/2 is square root. Square root of 4 is 2. And that's 9 over 6. So that's 3/2 plus c. So 2 minus 3/2 is 1/2. So we have y to the 1/2 is equal to x cubed over 6 plus 1/2. To get y as a function of x, I'll simply square both sides. All right, let's see how you do in this practice problem. We have solved for y as a function of x. dy over dx equals 4xy squared, and y of 2 is equal to 1. So let's give it a try. I'm going to divide both sides by y squared, and I'll multiply both sides by dx. We'll rewrite this as y to the negative 2 dy and 4x dx. So when I integrate, I get y to the negative 1 divided by negative 1. And this becomes 2x squared plus c. I'll go ahead and divide both sides by a negative 1, giving me negative 2x squared, again, just plus a c. Y of 2 equals 1 tells me that when x equals 2, y is equal to 1. So that gives me 1 equals 4 times the negative 2 is a negative 8 plus c. So 9 is equal to c. So we can say that this equation is y to the negative 1 equals negative 2x squared plus 9. Or if we reciprocate both sides because of the y to the negative 1, we're just raising both sides to negative 1 power, we get that. Okay, try this question. All right, so for this one, we again are going to be asked to do some analysis before we actually find the equation. Hopefully you were able to go through and do each one of these questions. If you haven't done them, you can do them one at a time before I do it, but make sure you practice it first before you're watching me. So pause the video if you still need to. All right, we're going to write the equation of the tangent line to y at x equals 0. Well, I know that y of 0 is negative 2, so that helps. All I need to know now is the slope. Because remember, the tangent line is y minus y1 is equal to slope times x minus x1. And we've already been given that the y coordinate is 2 and the x coordinate was 0. We just need the slope of the tangent line, which is given to us by dy dx. So 2 times 0 over negative 2 squared is just 0. Is y concave up or down at x equals 0? Well, to find if y is concave up or concave down, I need the second derivative. I need d2y dx squared. And here I need to use the quotient rule. Low, d high, minus high, d low, and that gives me a dy dx, all over low, low. Now, I don't actually need to replace the dy dx because I already know that dy dx at x equals 0. At x equals 0, the y value is negative 2, and we know that dy dx there is 0. So this is just 2 times negative 2 squared minus this whole thing, because dy dx is 0, also because x is 0, this whole thing is 0. And then negative 2 to the fourth is a positive 16. So this becomes 4 times 2 is 8 over 16 is 1/2. What this tells me is it is concave up at x equals 0. Let's go ahead and grab this equation for us so I can see it a little easier down here. We can make a slope field. All right, let's make a slope field. So we can see that whenever x is 0, the slope is horizontal because the slope is 0 there. Whenever the y is 0, though, we have a vertical slope. Or we might say that the function is undefined there because we can't divide by 0. But we have the derivative is undefined there, excuse me. So we have something like that whenever the y is 0. Whenever x is equal to 1 and y is equal to 1, I have a slope of 2. Whenever x is equal to 2 and y is equal to 1, I have a slope of 2 times 2 is 4 divided by 1. And then this would be 6, and it just keeps getting steeper. When x is 1 and y is 2, I have 1 times 2 is 2 divided by 4 is a half. Then here it's a 1. And then here this is 6 divided by 4 is like 3 halves. so a little bit steeper, and then even steeper still. And here we have 1 times 2 divided by 9. That is getting really flat, right? And then this is 4 divided by 9, and then this is 6 divided by 9, so it's getting a little bit less flat. And then 16 divided by 9, or excuse me, 8 divided by 9 is almost 1. So we see we have this kind of flattening out as we're going upwards. As I move up to y values of 4, 2 divided by 4 squared is 16. That's 1/8. So we're talking pretty flat stuff here, but it is still slowly getting higher. All right, now we look at the negatives here. The x values will start having a negative on top, but the bottom is still going to be positive. So it's going to be actually the exact same thing we had over here, but just, pointing in the opposite direction. So something like this. And then all right, now down here, we're actually going to be getting the exact same stuff as we had up over here because the y values are squared. So this is still going to be 2 divided by 1, and this is going to be 4 divided by 1. So, real steep. And then this is going to be 1 divided by 4, 2 divided by 4. So that's a half. And then this is going to be 4 divided by 4 is 1, and this is going to be 6 divided by 4, so still getting a little bit steeper. But then again, we get that pattern of it's getting less steep down here and then quite a bit less steep. And then these here will repeat as well. Again, just getting less and less steep as you go. So it starts steep and then it gets flatter. Okay, we're going to draw a solution through 0 to -2. 0 and -2. Well, what would that be? Well, that's going to be a flat line here until it starts to curve upwards, and it'll become vertical-ish before leveling back out again over here. And then on this side, it's going to have to again do kind of something similar. So it ends up looking kind of like that. Let's find the solution to this initial value problem. So to find the solution, we need to start with this information here. Having trouble with my scroll wheel here. It's getting a little carried away. And we'll add that y of 0 equals -2. Y of 0 equals -2 tells me that when x is 0, y is a -2. All right, let's move some things over. Y squared times dy is equal to 2x dx. All right, let's integrate both sides, and I get y to the third over 3 is equal to 2x squared over 2 is just x squared plus c. I'll go ahead and multiply by the 3, and I get 3x squared plus, again, just some c. I'll plug in -2 for y and -2 cubed, and then this becomes just a 0 plus c, so that is a -8 is equal to c. So we know our equation is y cubed is equal to 3x squared minus 8. Or that means the cube root, or 1/3 power if you want to use reciprocals. And there we have it. Okay, sometimes on the AP exam, you are asked to select a solution to a differential equation that is too challenging to solve. I don't see this too often. I think it might have been used to be more common. Well, instead, what you're supposed to do is simply check each multiple choice answer. So if you come across a differential equation that is not separable, then they're just asking you to check each answer choice, which seems time consuming, but that's the process. So the way I'm asking this question is I'm going to say confirm whether or not y equals 2 sine x plus 3 cosine x plus 4x is a solution to the following differential equation. So I have y double prime plus y equals 4x. If you have a mix of y double prime and y, you are not supposed to solve that by hand. It's not going to be separable. You can't do anything with y double prime. You can do y double prime equals 4x and then find y prime and then find y, but not y double prime and a y or y double prime and a y prime. So that's your indication that you're supposed to just confirm. So to confirm this, we just need to find these things. Let's find y prime first because we need it to find y double prime. The derivative of sine is cosine. And the derivative of cosine is a negative sign. So it becomes like that. And the derivative of 4x is just 4. I can now find y double prime, and I get negative 2 sine x minus 3 cosine x. And the 4 goes away. So now let's just replace this stuff in here. If I plug in y double prime, I get negative 2 sine x minus 3 cosine x. That's the y double prime. Now I need to add y, which is 2 sine x plus 3 cosine x plus 4x. And this is supposedly supposed to equal 4x. Well, I think you could see that the 2 sine x and the negative 2 sine x cancel out. Same with the negative 3x and plus 3x. And I'm left with simply 4x equals 4x, which is a true statement. So this must be the solution. How they get it, we don't need to worry about. But we do know it is the solution. And that's it for this lesson. And so I will see you in the next one. Be sure to practice.